You know the drill. You click pay with PayPal and poof, it's done. But have you ever stopped to think about what happens behind that click? It's a global financial machine of mind-boggling complexity. So how on earth does it all work? We're going to unpack the architecture that makes it all happen.
Okay, to really wrap our heads around the scale we're talking about, just look at this number, $1.5 trillion. That's how much PayPal processes in a single year. That's not just a ton of money, right? It's a monumental, almost unbelievable engineering challenge.
So that leads us to the big question, the whole reason we're here. How does a global payment, your money, zip across borders, bounce between different banking systems, and get scanned for fraud all in less than a second? I mean, how is that even possible? Well, we're going to find out. Let's follow the money.
All right, first things first. To really get it, we need to understand the fundamental problem that PayPal's engineers were up against from day one. They call it the global payment trilemma.
And here's the thing. This is what's so fascinating. These three goals are constantly at war with each other. Think about it. You need financial records to be perfect. Not a single penny can go missing. That's extreme consistency. But that takes time and processing power. At the same time, you, the user, want it to be instant, sub-second speed, and then you have to wrap the whole thing in military-grade security. Trying to do all three of those things at once, at a trillion-dollar scale, that's the real magic trick. That's the core of their entire system design.
Okay, so let's start our journey right at the beginning. Picture this. You're on some website, you're ready to buy something, and you see that familiar blue PayPal button. You click it. What happens next? This right here is the first and honestly one of the most brilliant layers of security. When you're typing in your card details, it looks like you're on the merchant site, but you're not. You're actually in a secure little window, an iframe, that's being served directly from PayPal servers. That means your actual sensitive card number never touches the merchant system, ever. Instead, PayPal just sends back this temporary one-time use token, something completely useless to a hacker, that basically just stands in for your payment.
And that whole process has a name. It's called tokenization. It's a really simple idea, but it's incredibly powerful. You're just swapping the real sensitive data for a non-sensitive stand-in. And this is a huge deal for merchants because it dramatically reduces their security burden. We're talking about all the headaches of PCI compliance. For them, this is a game changer.
Okay, so the token's been created. Now what? Well, that payment request, with the token attached, leaves your browser and heads out into the wild, into PayPal's massive global network. So how do they even begin to manage that traffic?
To handle this absolute flood of data, PayPal had to build their own custom system. It's called Meridian. And honestly, the best analogy is this. It's the system's universal air traffic controller. It directs every single piece of data coming in, doesn't matter if it's from you, a merchant, or even one of their own internal services.
So, Meridian isn't just one thing. It's split into two main parts. First, you've got the outer mesh. Think of this as the bouncer at the front door. It faces the public internet, handles security threats like DDoS attacks, and makes sure your request gets sent to the closest, fastest entry point. Then you have the inner mesh. This is like PayPal's private internal superhighway. It connects all of their different systems together, the ones in their own data centers and the ones running in public clouds like Google Cloud or AWS. It's basically the glue that holds their entire hybrid cloud world together.
All right, so your request made it past the bouncer and is now securely inside PayPal's network. But we're not done yet. Before a single cent actually moves, that request has to get past one of the most sophisticated digital detectives on the planet. And here's the kicker. It has to do it in the blink of an eye.
Less than 200 milliseconds. I mean, just think about that. That's the entire time budget the fraud engine gets to make a decision. Is this transaction legit or is it fraud? If it takes any longer, the whole user experience starts to feel slow. It is an unbelievably tight window to work in.
So what on earth can you even do in 200 milliseconds? A lot, it turns out. The engine is computing thousands of data points, what they call features, in real time. It's looking at the simple stuff, the static features, like the payment amount and currency. But it's also looking at dynamic velocity features, like how many times has this card been used in the last hour? It's analyzing your device, your location, even how you move your mouse. And most importantly, it's asking these complex graph-based questions like, hey, have we ever seen this specific device linked to a known fraudulent account before?
And this is where tech like graph databases, specifically, they use one called Aerospike, becomes their secret weapon. You see, fraudsters rarely work alone. They build these complex, hidden rings. A graph database is built to see connections. It can instantly spot those subtle, hidden links,
like say 10 different accounts that have all logged in from the same device, patterns that a normal traditional database would just completely miss.
Okay, the fraud check is clear. Phew. Now we get to the heart of it all, the money part. How does PayPal actually move the money and, at the same time, absolutely guarantee that its digital ledgers are perfectly balanced?
Well, because PayPal is built on hundreds of different little microservices, they can't just use one big single transaction. It would be impossible. So instead, they use a clever approach called the Saga pattern. The best way to think of it is like a project manager for the payment. This orchestrator manages a sequence of local transactions. Step 1, debit the buyer. Check. Step 2, credit the merchant. Check. Step 3, log the fee. Check. Now, if any one of those steps fails for any reason, the orchestrator's job is to execute compensating transactions, basically to perfectly undo everything that just happened, leaving the books exactly as they were. It's all about ensuring that consistency no matter what. But what if something goes wrong on your end? Like your internet glitches and you hit the pay button a second time. How do they avoid double charging you? This is so important. Every single request that goes to PayPal includes a unique ID, a special header called an idempotency key. If their servers see a request come in with a key they've already processed, they don't do it again. They just go, "Oh, we've seen this before," and send back the original successful result. It's a simple but absolutely critical safeguard.
And here's another key distinction you got to know. What you see, as a user, that instant confirmation, that's called the authorization. It's basically a real-time promise to pay. The actual movement of funds between all the different banks, well, that's called settlement. And that usually happens way later, often overnight in these big batches that are sent via super secure file transfers. So the speed you feel isn't the money moving, it's the promise of the money moving.
So, finally, let's look under the hood a bit more. Because, let's be real, none of this, not the speed, not the security, not the scale, would be possible without the incredibly resilient tech foundation holding the whole thing up. And here's a quick look, kind of like a cheat sheet of their tech stack. You'll see a lot of familiar names here if you're into tech. Things like Kubernetes and Kafka, which are pretty standard for big systems these days. But you'll also see those really powerful, custom-built tools we talked about, like Meridian for routing traffic and Aerospike for that lightning-fast fraud detection. And it's all running on this massive hybrid cloud infrastructure, mixing their own data centers with public clouds.
I want to call out one more really cool custom innovation here. It's called Hera. Remember Meridian was the bouncer for the front door? Well, Hera is the bouncer for their databases. It's a special proxy that sits in front of the database and takes in the thousands upon thousands of connection requests from all their applications and cleverly funnels them down into just a few hundred super efficient managed connections. This is how they stop their databases from just getting totally overwhelmed. It's a key reason they can scale old-school relational databases to handle PayPal's insane traffic levels. And maybe the wildest part of all, to make sure this whole system is absolutely rock solid, PayPal practices something called chaos engineering. And yes, it's exactly what it sounds like. They intentionally inject failures into their live production system. They'll crash services on purpose or deliberately slow down the network, all to test if their safety mechanisms and automatic failovers actually work as designed. I mean, it sounds crazy, but it shows a radical commitment to reliability. Because when you're moving this much money, even a few seconds of downtime is a catastrophe.
So, there you have it. From a simple, secure iframe on a merchant site to a global traffic controller, a fraud detective that works in less than a blink of an eye, and a self-healing foundation that they break on purpose, that is the whirlwind tour of how PayPal moves over $1 trillion a year. It really makes you wonder, right? What other invisible engineering marvels are hiding behind the